Good day to you. This is Galactic bringing you another science presentation in astronomy, which is a huge subject now, of course, and actually has two edges now, which science is attempting to unify. The two edges are easy to describe and to visualize. They're the inner edge and the outer edge. Part of my work is to see if there's a geometric relationship between these two that has not been detected so far in astrophysics or in quantum mechanics by well-directed, well-intentioned astrophysicists and subparticle physicists to unify these two areas. Very often, these two areas are characterized as the realm of electrodynamics and the realm of gravity. That is quite artificial and is part of the perceptual problem. Gravity, of course, is a macroscale force. It is not detectable at the subatomic level, but the effect of Einstein's discovery of relativism, which is basically the relativity in velocity, the measurement thereof, which has to do with measuring a time difference, which itself is not constant according to a frame of reference, which we're forced to in a measurement, that is, the center of measurement will be one locus in attempting to get a fix both on space and time at the same time. So it's at the same time and at the same place. That's called a reference frame, which has a center. What does this have to do with astronomy? Immediately, one must face the perception that they're not related at all, because they're at two opposite ends of a spectrum of scale. The quantum mechanical paradox has to do with going in and reaching a critical limit, a failure point in the measuring system, which is inevitable. This was to be expected, but now that we've reached it, having obtained enough technology to focus inward so far, with various technologies for exploring the inner range of the atom, that now we find that our number system is not performing as expected. And that's one way to encapsulate in some way the paradox involved in our measuring of reality. This is now a major topic, concentrating these days, at least in popular science, of course with reality, since that is a human perception. In astronomy, we're accustomed to looking out. And of course, in these 300 some lectures that I have been producing over the past 10 months, astronomy has been the topic, of course, which one would expect is looking out. Really, one does not expect to be looking in. You don't turn to astronomy to grab a microscope. So the initial perception of the relationship between quantum mechanics and astrophysics may or may not be apparent. The efforts to get what are called sometimes the theory of everything or the grand unification theory, essentially, just to sum up a very long and convoluted story, what is being attempted with these kinds of theories, which have the word grand and everything in them, is to unify subatomic physical geometry with macroscale geometry going to the edge. So we're talking now about the center and the edge. And why would we do that for the sake of astronomy? I think you know, but it's important to be, right now, you and I, on the same page as we finish up another tour of the universe, which I am very happy to conduct over and over again, since I learn something every time we go out on a tour. In our recent tours, because of the accelerating pace of our understanding that we're trying to gain and which I'm trying to share, at the same time as I learn with you, and believe me, that is true. I learn something every time I give these lectures, and I listen to my own lectures. Very often I listen to the same lecture more than twice, and lately I've been doing that a lot in order to review the sequencing that I'm undertaking right now, which is actually quite difficult, speaking objectively, because I'm attempting to address this area of research which is at the top. This is the Fermi edge of science. Absolutely the Fermi edge of science. This is where it's happening. And so for me to presume, even to explain what is already known in our attempt to see clearly the universe, I am attempting to probe an area which everyone at the top flight of science is trying to get. That has not been successful. Nobody even imagines or presumes there has been the slightest bit of success. In what? In unifying quantum mechanics with cosmology, both of which are attended with a certain paradox, which I claim are related. That is the assumption, is that the laws of physics are related at all levels. We have every reason to believe that, and no reason to believe that there is some other kind of physics. That is so well accepted that it hardly needs discussion, because it has been the basis of science since day one to the present day, is that physics is consistent. But it's very important now to be sure of our tools, because something has gone violently wrong with our system. There is nothing wrong with the universe, in the sense that we've made some mistake in physics itself. No. The scientific method has been successful. We know this in part due to the success of technology on Earth. That's redundant. Technology is limited to Earth because we can build things here. That is, we can machine things, including numbers. Calculus is a machining tool for numbers to make them rational. And without going into detail on that, which I've covered in previous lectures, it will no longer be possible for me to summarize certain guiding principles which have been established in prior lectures, which when I come to them, I'm going to have to breeze over these fundamental insights of science, which may be somewhat unfamiliar to you or questionable to you if you've never heard them before, but I assure you, I have no incentive or intention of misleading you in any way. And so from this point forward, and for the next couple of months, the nature of these lectures is going to be progressive. It has to be. I can't continue to re-summarize what's already been summarized, certainly not to the extent that I already have. In the progress of science, as we seek to explain things in the way that I'm doing now, that's very commonly done, you begin with a broad range of topics and, I'll just say, issues, and you try to narrow it in the way of summarization. You establish proofs for certain foundational principles, and you work inward. And then you take the principles which have been crystallized, and you use those for another synthesis which is more intensive. It takes less time because you're familiar with the notation, the representation, the terminology. The mathematics and geometry perhaps underlying it is now inside your head, so you don't have to keep asking questions. which at the initial stage are absolutely essential. It's why professors and teachers are unanimous and uniformly emphasize to the point of becoming tedious in their repetition. They keep telling you to ask questions, and it's very important that you obey that. You have to be brash. You have to question at first. But the objective is to allay your doubts, not to get you to believe something. That's a trap. But to get you to know things that you didn't know before. Now, of course, that's quite a... you better know whom to trust if you're trying to get information from a man. But that is how we do science. We finally have to share what we know. This is a collaborative issue, a collaborative enterprise. In a sense, this is all humanity is doing this. And when you look at someone like me or anyone who's doing science, we're just a piece of the puzzle. We're contributing. We're participating. What I'm doing is quite humble and simple. It's a very simple approach that I take. What do we know about the universe? Well, as you can imagine, due to the nature of the subject, that is likely to be an expansive topic. You're not going to just sum that up in a short lecture, like, well, there's a lot of stars. There are going to be further questions going to infinity, essentially. But that's not what science deals with. We don't deal with unknown concepts like infinity, because you can't understand it. What you can understand is structure. Structure combined with measurements. And that really is the legacy of science. So what have we discovered? What have we measured? And what structures are we aware of that can be communicated so that you can know them too? That is, you won't have to believe what I say or what Einstein says or what any man says. You listen to what a scientist says, and then you do it. You have to do what that scientist did. Now, obviously, that's not always going to be possible because at the limit, you're going to need multi-million-dollar telescopes and spectroscopy equipment. Spectrographs, telescopes, you're going to need interferometry, you're going to need megabucks. But happily, because science is a collaborative issue, you don't actually need to own that equipment. You can rely on men who are using equipment that's extremely expensive to get the answers that they want for all of us. And then you can know it too. Now, you don't have direct access unless you go to the telescope and spend days taking the same readings. But again, you're probably not going to get that opportunity. Well, strictly speaking, you shouldn't need it. If the scientists are doing their job right, they get the money from somewhere. They build the telescopes and microscopes, all the equipment needed, all the processing needed from supercomputers to get answers to certain intermediary questions about macroscale structure in the universe and about subatomic structure really at the center of things. So we're looking at the center now as well as the edge. Why? Because that's how you understand light. Light is a phenomenon that occurs at a different scale, obviously, than galaxies, superclusters. The CMBR is a form of light. That is a glow from the edge, we believe now. It's coming from all directions at the same frequency, within a very tight range of attenuated, weakened light that's just glowing at a fixed, although low frequency, in all directions, seemingly coming from the edge. So that is the physical limit, so far, the Fermi edge, literally, of what science knows about the universe as such. Going in, I'm sure you're aware, we've made equal progress in the reciprocal direction. That word that I used, reciprocal, is accurate. it's the reciprocal direction. And we'll begin there. Now over here, just to have something so you can see something while I'm talking, we're going to be covering what it says there, the forces in Boscovich theory, with assistance of Dragoslav Stojkovic. The man who executed this is Roger J. Anderson. It's a talk, as you can see, based on some work by another man named Augustus Prince. This is right now the Fermi edge of science. What this journal article is talking about is the Fermi edge. This is where our understanding is opening up again for the first time in 70 to 100 years on both aspects of astronomy. This is astronomy. That's all I do is astronomy. I don't do earth sciences. I don't do psychology, philosophy, or religion. What I do is pure science. Pure science. The facts only, ma'am. The knowledge that we actually know, not a guess, well established. You can check it yourself and use that to get understanding. This stage of understanding is the goal of science. Why, you might ask, would anybody want to make that their goal? Understanding is a human concept. It's not really strictly science. It's the intersection of physical truth, which we call physics, the universe, the measurable, structured universe. It's the intersection of that with what we're capable of reflecting in our mind. And there's been a lot of talk about that lately in terms of such philosophical conceptions as consciousness, what the mind actually does. And it just goes all the way down the rabbit hole. And this has come up in upper echelon physics so that we sound like philosophers sometimes. Certainly Einstein and Bohr did. But that's a necessary part of science because we're transitioning from the integrative phase to the solution phase. In other words, we're about to get our answers. We know that now, but we haven't done so yet. Again, although this becomes somewhat philosophical, at this stage we cannot avoid metaphysics to some degree. It's normally unwelcome. Usually scientists are just doing their work, working out things. They're not really talking about philosophy, psychology, how it affects the humans of Earth. We're not normally doing that, but eventually we have to. The purpose of science is a human purpose. It's not happening by itself. We're not automata just working out equations to leave for posterity and hope that, the future generations get something out of it. That is how it effectively works. But at no time is any man storing up knowledge like storing food underground for the next generation of ants. We're not ants storing up stuff for the next generation. We're not really trying to save the earth or save humans or make life better on Earth. We're astronomers and we're essentially divorcing ourselves from the Earth completely. You can't. Of course you can't. You're human. And that's why I say this is a human issue, which is a complicating factor now. As I've discussed in a series of lectures on the Nobel Prize for Physics in 2022, the most recent prize in physics by the Nobel Prize panel was given out for nothing more and nothing less than a philosophical point of view. It was given to three men, one of whom was Alain, that's a French last name, who was directly involved with John Bell. And John Bell was trying to solve a philosophical issue with his very famous Bell's experiment, by which he was able to establish He didn't actually perform the experiment that he devised, but over the next few decades, several men were able to devise experiments that matched what Bell predicted you would be able to discover about quantum mechanics. So John Bell is now immortal. He is the direct successor to Dirac and Einstein in trying to probe this incredible paradox. And John Bell's law of inequality is now well established. And John Bell's, he has two theorems that are now well accepted. And what he was trying to do, just to recap, you may already know this, but forgive me, I do need to give some bracketing information for where we're going, which, by the way, is to complete the flight of the photon. But in attempting to get at the nature of the incredibly important debate between Niels Bohr and Albert Einstein, raging on into the indefinite future, there's every reason to believe now, at least in Stockholm and around the United States and around the world, the astrophysicists and the quantum mechanists are settling back in their chairs now and giving up. They're not going to try anymore to solve this problem. They're going to say that they're trying to solve it and continue to spin the hamster wheel, making no progress. There has been zero progress in 70 to 100 years in quantum mechanics. Now, you would not even know or believe that from the news reports daily all over the internet, just flooding the internet with, you might say, propaganda, since it's so one-sided, but it's all on the side of Bohr. And what did Bohr say that contradicts Albert Einstein? Bohr said, you don't need to worry any longer about how it works. So Bohr turned into an anti-scientist and decided to give up. And that is perhaps acceptable to you. It certainly is not acceptable to a real scientist. And so Niels Bohr is in disfavor right now with Intergalactic, that's for sure. But Albert Einstein has already been justified. Nobody knows that yet except myself. But Roger Boscovich fully supports Einstein and gives the thumbs down to Niels Bohr and his Copenhagen theorem of futility. And science no longer works, and we're going to have to accept probabilities from now on. That's ridiculous. And so Stockholm was wrong last year, and they gave out a Nobel Prize for pseudoscience. We'll be keeping tabs in the upcoming year as we approach October again to see what the Nobel Prize Committee comes up with this year to give out a meaningless award, probably to celebrate anti-science again. But we here at Intergalactic, that is myself, and anybody who wishes to join in, we're going on with what Einstein taught us we can know, and we're going to know. We're going to figure out the quantum paradox. I already have. And I have every reason to believe that I'm the only man on Earth right now who understands the quantum paradox and can teach it to children. Just bypassing the PhDs and the Nobel Prize laureates, you can sit down in the back while I teach people willing to listen. Now, I don't take an attitude about that, although you may suspect that is an attitude. No, I'm reconciled to the situation on Earth. I'm reconciled to the situation in so-called science. But I happen to know that what is being practiced as science today has a different name. It's not natural philosophy, as Boscovich, Leibniz, and Newton practiced. It's not natural philosophy. It's no longer human. There no longer are human answers being sought. And so science has completely changed course. It's now technological. It's now strictly for the toys. It's strictly for the money. It's strictly for the governments and their agendas. In the meantime, there's a whole sociological framework that needs to be supported on Earth so that the carnival can go on for the governments. And that's the nature of life on Earth now. The governments run it, and everyone else is a slave. And now science has been taken in the net, and that's why you're getting so much propaganda. It's so you'll never find the truth. The truth is not good for slaves, according to the governments. You can give the slaves entertainment. You can allow people out on the internet, like Dr. Sabine Hossenfelder, totally useless and meaningless to science. Dr. Sabine Hossenfelder is one of my heroes, and I think she's doing a great job. I think she's an excellent astrophysicist. She's in the industry, and she has millions of viewers who tune in, as I do, to watch her just smash cream pies in these goddamn physicists' faces who are lying to you in their teeth about black holes, big bangs, expansion, parallel universes, multi-universes, strings, none of which is science. And I saw this coming when I was in high school, because natural selection, against my objections and everyone else at the high school and college level in the 70s, we lost. Science lost the very first fight. In the 1960s, the monkey meat theorem became law. In the United States of America, you're either descended from a monkey or you're out. You either fess up and you tell your children, yes, you're from monkeys. If you don't do that, you will be ostracized and you'll end up in the gutter. You won't get an education. You'll be denied any part in the United States economic system unless you agree with natural selection. Otherwise, you're a Bible thumper, a God freak, and someone who cares about humanity more than about money. Okay? It's about money. So, how does this affect astronomy, astrophysics, quantum mechanics? It's all government funded. And what do governments do? What's their motive? Yeah, not truth, not humanity. And they're the ones, led by the United States government, the most amazingly powerful government that's ever hit the face of the earth. Well, we know what to expect next, then. And it's not going to be fun. But for now, it's already not fun, because you can see where the world is headed, where the United States is headed, where science is headed, where our fate and destiny is headed right now. You're blocked from any way out of this death trap. I'm here to tell you that no, you're not blocked. You've never been blocked. You'll only be blocked if you want to stay blocked. If you don't want understanding, you don't believe in truth, you know there's no hope, you've already given up, well then you belong with the astrophysicists then, because they've given up too. But if you're not getting money for it, nobody is going to pity you. You've got to get money for your lies. That's what they do. They'll tell you about the Higgs boson, gravity waves. The astrophysicists will tell you they photographed the black hole. They know that the universe exploded from a fiery ball out of nothing and now is expanding in a totally anti-scientific, anti-physical, anti-understanding, anti-truth way. And it's just like natural selection. You either know about the Big Bang and you say yes, you start nodding your head and smiling like a smiley face, or you're out. You're out. No money. Do what the government says or die. That's already happened. So everything you're getting on the internet, everything from the professors in the universities, everything in the books about quantum mechanics and astrophysics is totally off course. But that doesn't stop us. That doesn't stop men like me. We learn to see through that. A scientist has to learn to see through BS and to go on anyway. And then we have to stand up to the system, just like Galileo did, just like Einstein did. All of these discovery scientists faced enormous pressure against them. Why? Because you're upsetting the current model. The current model is what keeps society held together by a thread. But when you have too many people disagreeing with a common paradigm, you're on the verge of revolution, and governments learn to suppress that kind of action. They don't like truth. They don't like understanding. They don't like the slaves poking holes in the paradigm. So what might make me so apparently upset is the current state of common knowledge about the universe. That if you want to even begin to ask a question about the universe in any direction, you're going to have to start with a cold, dark lambda model based on cosmological expansion, which is already pseudoscience. But that's what everything is based on. We've traced that back to the actual source of where they get their ridiculous theories from about the beginning of the universe and what the universe is doing now. That is physics. That would be astrophysics. What do they actually say? Unbelievable stuff. Just to begin, right out the gate, where you're most vulnerable. Hey, Mr. Astrophysicist, what do we know about the universe? Oh, they're delighted now. They can feel the money going into their pocket. And they're going to get approval from their college, the government, everyone loves them. Tell the poor bloke what we know about the universe. Well, the first thing you need to know, Sam, or whatever your name is, it's expanding. Oh, wow! Yeah, now everyone's excited. Yeah, it's expanding. And you ask, as anyone might be expected to ask at this point, what's it expanding into? And then they just glare at you. It's just expanding. Well, it has to be expanding into something. It's expanding into infinity, or a blackness, or a darkness, or an anti-bang, or a parallel this, or an upside down that, or an inside out that. And then they push on. Let me tell you about these equations. And you're still furrowing your eyebrows at them. What's it expanding into again? Weren't you listening? It's expanding into anti-gravity malarkey space. It's going into Riemannian, Minkowskian, fluctuating inside-out space. Oh, we'll get to that, don't worry. First you have to learn these equations. Well, there goes $100,000 in 16 years of your life as you catch up with these assholes to find out they don't know anything. That's not quite true. They have to have a basis for their lies, or they wouldn't believe it themselves. So what have they convinced themselves of about the universe that makes them so goddamn certain that it's expanding? Well, I covered that in several lectures, including one very recently that I think sums it up even better. It should get better and better if I'm doing my job. I should be able to tell you why these are lies. So the first thing you have to understand there is it's based on one measurement. The expansion of the universe is based on exactly one measurement, redshift. Well, we explored that and exploded their theory. Now today, what we're going to do, my intention here is to wrap up our series on infinity and our series on the flight of the photon, which I began yesterday. If you didn't see yesterday's video, don't worry, you don't need to see it, although it certainly would help. What is the propagation of light? This is how we know everything about the universe. The propagation of light. We use telescopes to see the sky. We use spectrographs to get spectrograms and we use telescopes to get portraits. We use various tools to measure light to understand the universe. There's another tool, and really only one other one, unless you can think of another one. It's gravity, correct? That's considered to be a universal principle. Well, as we've learned, partially with the help of Boscovich, Newton got gravity wrong. And I think that that's the biggest shock, because Newton's gravity is revolutionarily good. He does have a very good approximation of gravitational force, but it's an approximation, and it's never been fully accurately measured. That is, the principle of gravity, which is a centripetal force. It's a force that draws into a center. Now that's obvious, but it needs to be stated obviously now, because you need to see this clearly to understand Newton's mistake. Newton was not quite old enough in terms of history to get gravity. What he did is he formulated an extremely good approximation with linear algebra. And to do so, he had to expand the concept of the calculus, since the only way to understand a circular or spherical function is with calculus, because we don't have any geometry of curvature. The geometry of curvature that we pretend to have is based strictly on straight lines. And that's a very key insight. That will lead us to the quantum paradox and the mistake made in astrophysics, whereby they misrepresent the universe completely. It is that basic. We knew it would have to be something very basic. But as for MOND, M-O-N-D, modified Newtonian dynamics, no. We don't need modified Newtonian dynamics. It will end up being modified Newtonian dynamics, but until you get the right geometry, you're going to have new variations of the mistakes in Newtonian dynamics. And Einstein came along, came up with a much more accurate, much better linear formulation of gravity that has exactly the same failings as Newtonian gravity. You're using the wrong number system, you're using the wrong geometry, you're using the wrong mathematics, the wrong algebra, and worst of all, you're using calculus, which means you've failed. Your calculus will not get these answers. I know that, and I've proved it, but I need to prove it again and continue to prove it, because this is it. This is the turning point. So, Dragoslav Stojkovic, that is a Croatian name. Ruđer Bošković is Croatian, so Dragoslav knows how to read Roger's language. Well, Roger actually published in Latin, and for that matter, so did Newton. They all did back then, but Dragoslav is an amazing scientist. He's way up on Boscovich theory, and Roger J. Anderton has affiliated himself with Dragoslav Stojkovic in exposing some things about the Boscovich theory, which let's take a quick look at some of this. This is the Boscovich curve, of course. It says down here in the caption, contemporary verifications of Boscovich's curve. Okay, let's make sure we know what we're looking at. I've shown this in several previous lectures, but let's just recap to make sure you are literally on the same page here with me and with Dragoslav and our friends here. What do they say that's of great importance to us looking for truth about the universe? What does this curve mean? This is a 2D projection of a spherical phenomenon. And so what does that mean? Can we visualize this any better? Yes, we certainly can. Right at the meeting point of the two orthogonal lines is a letter A. And you can barely see it there. I don't have a pointer, but you can see where the A is. It's where the horizontal and vertical lines meet. What does that represent? Well, there are two lines, so rather than say what the intersection means, we should say what the two lines represent. Those are called dimensions. That is inaccurate. Let me say it better. Those are two linear dimensions. Linear dimensions are traditionally orthogonalized, in which case you have a 2D graph. Otherwise, if the two lines are not orthogonal, you have an affine graph. We don't need that, although that has certain geometric value. That would mean that the two lines that meet at a point are not necessarily at 90-degree angles. But when they are at 90-degree angles, we can use the graph for very intricate and arbitrarily precise measurements. Arbitrarily precise down to a limit. And that limit is on this graph, and I'm going to show you where it is because it is the quantum. It is also infinity. It's also the measurement problem. It's also the collapse of the wave function explained, and it's also the relationship between space and energy. And time is in there, and I'll show you where that is too. This graph is completely explanatory of subatomic particle physics, with one exception that Roger himself notes. If you look closely, I'm going to see if I can expand this a little. Yeah, let's get this a little so you can see it better. Let's home in on that middle A. Now this is a poor rendering, and so you can see it's getting grainy. But I think you can see that pretty well. You see this label here, repulsive force. What is that labeling? The vertical line, I'll show you what it is. The vertical line is the center of an atom. Okay? Technically, and according to Roger Boscovich, who did not know about the atom because nobody knew about the atom, he calls this a particle. And that turns out to be an incredible insight. This is the diagram of the relationship between two particles. Particles. If you know anything about quantum mechanics, you know that that is one whale of a loaded word now. Because nobody knows what a particle is any longer. We only know about particles indirectly. But when we go to measure them, we can't. We can either get a position to a certain arbitrary degree of accuracy, or we can get momentum to a certain arbitrary degree of accuracy, but we cannot get both, and we cannot get either beyond a certain degree of accuracy. And those are two separate problems that have never been solved. The path of the particle is on the horizontal line. That is the linear distance separation dimension. It's the dimension of linear space. That is the horizontal line. Okay, now comes the hard part. What is the vertical line? The label here indicates that the vertical line represents repulsive force. Now that's not exactly true, because down here it says attractive force. Good heavens. So, well, oh my goodness. There's attractive, oh boy. Well, there's attractive force. So when this curve is below the horizontal line, it means that the particle is undergoing attractive force. So let's say the particle is way over here at the right, at C. You can see the big C on the horizontal line at the extreme right. Following the path of the particle toward A, it's going to contact the particle at A if everything goes well. Well, it's going to go in a curvy fashion, even though the particle is going toward the other particle at A, from C to A, from right to left. You can see that the curve shows that it's encountering both attraction force and repulsion force, depending on how far away it is. If it's way over here at C, then the particle itself is on that line. It never leaves that line. But down here, just below the horizontal line where it ends at the right, you'll see the beginning or end of the curved line. We're thinking of that as the beginning. So C is where the particle enters the graph on a straight line course toward A. However, it's being attracted, and you could think of it, the particle as being under the influence of an attractive force. In other words, the particle does not have its own velocity, but it has a relative velocity because particle at A is attracting the particle at C. That is, they're mutually attracting. Okay, so you got that. So when it's down the curved line, as it dips below the line coming into the graph, shows that it's accelerating. The particle is accelerating, and so it's achieved its maximum speed down at the bottom of the graph, correct? And then it starts to experience a repulsive force, and so it starts to slow down. And it keeps slowing down until it intersects the line at R. That is a measurable point. That is a point on the horizontal line. But it's important to realize that that is not a point on the curve. The curve does not have points. It's simply a curve. It's a relationship, not a location. The locations occur where the curved line intersects the horizontal line. Now that may be just a little bit baffling. I know it took me just a little while to visualize this in the correct mode, the correct fashion. The particle is going directly along the horizontal line from right to left, and it's encountering attraction at first, and then it's repelled, and then it's attracted again, and then it's repelled. Well, you might think, what if it can't get over one of the humps? There's two answers to that. It depends on if it's not making it over the bottom hump, or if it's not making it over the top hump. The first hump goes down, correct? That's a maximization of attractive force. That's equivalent to maximum velocity if we're following the particle on an actual traverse. It's now at maximum speed. And so it's directly above S, but going at high speed. Now as it continues forward, it's being repelled. And so it's slowing down. And then it passes the line and goes above the line, which means that the repulsive force is dominating. And so it's slowing down until it reaches a minimum. This is kind of upside down. We usually think of the minimum as being at the bottom rather than the top. But you should be able to simply flip it over in your mind. This is something you have to get used to. Otherwise, you can't read it right. So it reaches the top hump, where it's now at a minimum repulsion. And so it starts to accelerate. Well, what if it doesn't make it? What if it reaches near the top, but doesn't have enough impetus to get past the minimum at Q? The minimum is at the top of that curve, so forgive us all for that, but this is somewhat upside down from intuition. But at the top of the curve, it's at a minimum of repulsive force. So now it would start to accelerate again, but what if it doesn't make it to Q? Then it will stop. It will stop somewhere before Q because it's being repelled, and it'll start going backwards along exactly the same curve until it stops again. And then it will settle and stay there. And don't forget, this is a projection, so it hasn't halted. It merely has halted on the linear axis. It's not making any further progress, but it's not being pushed back. That is called an electronic orbital shell. It is the Lagrangian point in a spheric system. We can see that in the solar system, there are 5 Lagrangian points for any two-body system. In the closest two-body system that we know of, the Earth and the Moon, there are 5 Lagrangian points. These are places in empty space where this force curve proves that there's a place you can park a vehicle and it will stay there with respect to the two-body system. That's called a Lagrangian point, and the James Webb Telescope is parked at Lagrangian point number 2 of the 5 Lagrangian point two-body Earth-Moon system. So there's a little perspective on what this curve is capable of explaining. It explains the atomic orbital shell system. Each one of these curves is an atomic orbital shell. That was not actually discovered for another 150 years. But you can see right here, incontrovertible evidence, that Roger Boscovich knew everything there was to know about quantum mechanics 150 years before Bohr. That is one of the most remarkable secondary discoveries in the history of science. That Roger Boscovich knew quantum mechanics. So you might want to pay attention to whatever Roger has to say about that. Now let's go on a little bit so we can kind of pick up the pace a little. I don't want to wear you out with a lot of stuff that you may not seem connected with the flight of the photon. But let's just take a look at this to see what these guys have to say. Look at that. Number 1, the electron atomic nucleus. There's the Boscovich curve weaving its way through an atom. And those circular lines, those are the spheric orbital shells. Look at the one at the center. Does that look different? Look at how that curve goes right through it. You know what that is? That's the nucleus. And so this describes the strong force at the innermost curve. That shows the relationship between two protons. The first dotted line is the first atomic orbital shell. And then there's another one with like 4 lines, so it looks like a thick curved line, intersecting the Boscovich curve and intersecting the horizontal axis. So we have 3 representations of one single point on the line. For every one of these curves, including the circular ones where they meet the horizontal axis, which is linear separation in space. That's all it is space on the horizontal axis. Now, take another look at the innermost curve, where it shoots asymptotically vertically towards D, right to the left of where it says repulsive force. Down here where it says distance, the curves go up and down, up and down, up, down to F, and then up! Up and up and up. Up, up, up. And does not come back. What does that mean? That means the strong force. It is a particle as long as you say something else, because it certainly is not a particle. So why are we so uncertain? Well, is it or isn't it? That is called the quantum paradox. It is, and it isn't. You can say it's a particle, but if that's what you say, you're wrong. And you could say it's a wave, and if you did, you'd be wrong again. But it has to be one or the other. It can't be both. It can't be a particle and the wave. Yes, it can. It is. Exactly both. And that's called a paradox. It can't be both by definition. Well, we need a new definition then of reality, don't we? That's exactly what we need, is a new definition of reality. Well, what's wrong with our old definition of reality? What is wrong with our old definition of reality, called Newtonian mechanics, extended to Einsteinian mechanics? They made the same mistake. They had no choice. Don't blame Einstein. Don't blame Newton. But Boscovich saw through it, in between Newton and Einstein. Newton did not get it right. Einstein did not get it right. They're separated by about 150 years. Actually, more, about 200 years. But about 50 years after Newton, Boscovich got it right. Well, then why didn't Einstein get it right too? Because nobody saw that Roger Boscovich got it right. That's why. Now, in his day, Boscovich was the most famous scientist by far in the world. Once Newton died and Leibniz died, there was kind of a vacuum. Because those two men, as you well know, revolutionized linear algebra with their separate discoveries of the calculus. We'll be right back. This is Anagalactic, bringing you the secrets and truth of the universe that nobody will ever tell you. I started out by telling you things that science has discovered that you don't know because you're not allowed to know them or something like that. But now it's branched out because I've been blessed with a discovery vector, a new geometry, culminating in a new number system, which utterly surprising to me. I found out about 6 months ago in the middle of this discovery vector that Roger Boscovich already has the algebra for my spherical space. And his force curve is the answer. The reason why the force curve does not instantly supply the answer to physics today, now that it's been rediscovered, and it's a match on quantum mechanics, absolutely he got it. How come nobody is using it yet? It's not just due to social pressure and governmental shit. It's not just that. It's that he didn't have a spherical geometry. He was still using linear geometry. It's a miracle that Boscovich figured this out simply by having absorbed the calculus of Leibniz and Newton. He didn't even use the calculus to get this force curve. He got it strictly with linear algebra. That's a greater accomplishment than Einstein made. Einstein was a hack compared with Boscovich, because Boscovich got the answer. Einstein just rehashed Newtonian linear algebra to get the world's worst answer for gravity. And the Einstein field equation is doomed. It is incorrect, and everyone knows it's incorrect. It's a great improvement in approximation on Newton's formula, but nobody has ever figured out space-time. Never. Everyone in the industry, I've checked, everyone in the industry thinks that space-time is curved. That is incorrect. No, it's not. But one of those is curved, either space or time, with respect to the other. And in the next lecture, I'm going to show you that could be either one. It depends on which aspect of the universe you're talking about, whether you're talking about time-space or space-time, because you need both to balance space and time completely on chirality. Because space is curved. Space is curved by protons. Protons curve space. Well, if they curve space, they must curve it in a direction, right? Yes, in. Protons curve space in. Well, that makes the universe imbalanced. Because now, according to Emmy Noether, you have an in component. Those electrons are trying to get in. They're not trying to get out. They're trying to get in. And they can't, and so they orbit around the protonic shell. The protonic nucleus. But that's only space. You're only talking about space. Space is curved. Well, that means you need anti-curvature, because every action implies an equal and opposite reaction. So if space all through the universe is being curved inward, there must be something that's going out to compensate. Emmy Noether proved that and got the Nobel Prize for it. And Albert Einstein praised her for it. Loved that woman, so do I. She got the symmetry of conserved force. Boscovich got the curve of force, and he showed how it balances two infinities, something that's never been done. I discovered that from his curve. And all four infinities that I identified, that are the only infinities known to man, are all on his curve. The two infinities of time and space are at the edge, going out, asymptotically, and the two inner infinities that we call the quantum, the infinitesimal of time called the tempuscule, and the infinitesimal of space called the corpuscule, or corpuscle, those two are infinities going in, and they balance on Boscovich's force curve. And that explains the quantum paradox completely. Just using two lines, one of them straight, one of them curved. And that explains exactly what the quantum paradox means and solves the equation of universal electrodynamics identical with the gravity force. And that's the end of this phase of science. And for the next few months, I'm going to be expanding on the greatest discovery sequence ever to be made in the history of science. Through Roger Boscovich, Max Planck, Albert Einstein, John Horton Conway, and myself. I'm the unifier, because I got the geometry. Not even Roger got that. And certainly nobody else has. But if anybody had been able to get at the new geometry, it would have been Roger. He didn't. That had to wait until 2022. And I discovered spherical geometry with the two-number system that has time and space as two different data types in an orthogonal relationship that completely describes the universe to an unimagined threshold of comprehensibility. You'll never get it from popular science, the current astrophysical generation, or the quantum mechanists. Completely failed. I got it. We'll be right back. Stay tuned to Anagalactic. That's 1 hour and 50 minutes. I apologize for that. But I have to desist now because I'm worn out. Again, in the next lecture, I'll attempt to lower my voice level and keep an even keel, not tell you about little girls being raped in Afghanistan by the United States monsters, or the destruction of all hope on Earth by bastards like John Krakauer, who who deserves either to be executed or shot to Mars or sent to Russia to get him out of our land. A person who is against all human rights for the sake of lining his pocket and being admired. Happy, happy, joy, joy. We'll be right back. Stay tuned.